we call R the basis of the distribution. It is the second most important property of the distribution next to the quantity that we look at. In our case, this is of course the particle size. In simple words, R determines the metric used for the amount of particles. This means it defines what exactly is 100% of the particle amount. For example, we can define as 100% the total number of particles, e.g. 100,000 particles, or we can define as 100% the total mass of particles, e.g. 5 kg. As you will see, this is of fundamental importance, as you will understand with an example in a minute. R can have integer values, meaning 0 for the size metric to the power of 0, meaning a dimensionless quantity, 1 for the size metric to the power of 1, thus a length x, and so on. Clearly, R simply indicates the power of x that is used as the basis for the distribution. Consequently, R indicates a number based in case R is 0, a length based if R is 1, an area based if R is 2, and a volume based if R is 3 distribution. We can best illustrate this with the following example. Consider a bidispersed powder with 9 small particles with diameter d1 0.2 mm and 1 large particle with diameter d2 1 mm. If we consider a distribution with the basis R equals 0, so number based, we see that the relative number based amount in class 1, i.e. the small particles, is 0.9. So 90% of the particles, number based, are small. However, if we consider a distribution with the basis R equals 3, so volume based, you will see that only 6.7% are in the small class. Clearly, the basis of the distribution is of great significance. We finalize the discussion of this slide by summarizing the naming of the different distribution bases. Once we have understood the basics of the basis of the distributions, we will see that we can also convert between different distributions. Let us therefore look at the definition of the number-based distribution again. We have denoted the number of particles in each class with delta Zi here, and the total number of all particles is Z. As you see, these quantities are connected to lowercase q0i. We can do the same for the volume-based distribution as shown here. In case we want to now calculate a volume-based distribution from a number-based distribution, we simply have to insert into the definition of the volume-based distribution the correct variables. If we use as particle volume the size of the particles cubed, note we could also consider the prefactor for spheres, which is pi over 6. This would not change the results in any way. We will arrive at this relation here. Last, we simply have to insert the definition of the volume-based distribution on the left-hand side, and voila, we can relate a number-based to a volume-based distribution. Please note that also a conversion between distributions of a different basis is possible. Measurement errors can be amplified by these conversions. This is because not always the volume equivalent diameter can be measured, but some other equivalent diameter. Unfortunately, we do not have time to discuss this further. To finalize our discussion of distributions, let us consider another example. We here aim at calculating the outer mean diameter of a polydispersed distribution. As you already know, the D32 or SMD is the diameter of a sphere with the same specific surface area SV as the whole particle population. Thus, we simply have to insert the definition of SV as you see here. Again, SV is the total surface area divided by the total volume. Both quantities are easily calculating using a number-based distribution for our example here. Note, we have removed the factor pi from this equation since it anyhow cancels out. After some math, we arrive at this equation here. Another mean diameter that can be easily calculated is the arithmetic mean diameter. Again, doing this using a number-based distribution is straightforward. Let us underline these results with some numbers. Therefore, we consider the same powder as before. We arrive at an SMD or D32 of approximately 0.79 mm as well as an arithmetic mean diameter of 280 micrometer, which is significantly less than the SMD calculated before. This again stresses the importance of a precise definition of the mean or average diameter we are interested in. Without this piece of information, the result is simply not well defined. Let us now move on to the next topic, which is concerned with continuous distributions. As you already know, they describe an ensemble of particles via an analytical expression. This slide summarizes how these distributions are characterized and constructed, namely from two parameters. The first one is the characteristic size of the distribution, and the second parameter characterizes the width of the distribution. These are very general definitions, so let us now look at some frequently used two-parameter distributions. A distribution you are possibly familiar with is the normal or Gauss distribution. As you might know, the two parameters are the median, in our nomenclature this is called the x50, and the standard deviation x. This distribution is gray on this slide, and this is for a reason. It describes particle distributions not very precisely. You will see this if you try to approximate experimental data for particles. Also, please note that distribution that we are looking at is typically applied to a volume-based distribution. However, and of course, it can be also applied to distributions having a different basis. A distribution that is very often used, and this with great success, is the logarithmic normal distribution. It has a similar structure as the normal distribution and approximates real-world experimental data of particulate systems quite often. The other two distributions that I would like to mention are the power law and the so-called RRSB distribution. The latter is quite often used, while the former is more of theoretical interest. Let us now dive into some details of these distributions. First, let us have a closer look at the log normal distribution on this slide. What we see here is the expression for this distribution, specifically for the frequency distribution and the two parameters already seen before. Note that the mode diameter, i.e. the particle size with the highest frequency is not identical to the median x50, but has a somewhat different value. As you may anticipate, this distribution has the drawback of a relatively complex expression, especially for the cumulative distribution function, which is not shown here on the slide. However, the advantage is that the specific surface area can be easily calculated from its parameters, as shown here for the volume-based and here for the number-based distribution. Let us now move on to the next distribution, which is the famous RRSB distribution, which is short for Rosin-Ramla-Sperling-Bennett distribution. As you can see here, the expression for the cumulative distribution is quite simple. The modal diameter is also quite simple to evaluate, and also the characteristic size x prime as well as the median can be easily calculated. Note that obtaining the parameters of this distribution from experimental data is very simple, as you can see here on the graph. One can easily linearize the cumulative RRSB distribution, taking 2 times the logarithm of it specifically, and hence parameter fitting can be done with simple linear algorithms, or more traditionally, even graphically, as you see here. Because the RRSB distribution is quite popular, we will have a look at it in an example.